What if the key to unlocking a new frontier, the colonization of space, isn't just a new kind of rocket, but a new kind of thinking? Quantum computers are on the cusp of another breakthrough. It's a complete rewrite of how we understand computer technology. It's being developed in labs right now, funded by billion-dollar bets, and driven by a single idea: leverage quantum mechanical phenomena to solve currently unsolvable equations. If future quantum tech can crack impossible problems, like energy abundance, or even rewriting life itself by combining AI and CRISPR, then, can we build the tools to set humanity free? Can quantum computers solve the equations of near-light-speed propulsion systems, or even faster than light-speed travel? Let's find out. To colonize space, to travel farther, survive longer, and build smarter, it might just be the technology that makes the impossible inevitable. But before we warp ahead, let's unravel what quantum computing actually is. Classical computers, the ones we use every day, operate on bits, binary digits, zeros and ones. These bits are like tiny light switches that are either on or off. Quantum computers? Well, they use qubits. And that's where things get weird. A qubit can be a 0, a 1, or both at the same time. That's called superposition. It's like flipping a coin and having it land on both heads and tails at once, until you look, until you observe it, only then does a head or tail appear. But that's not all. Qubits can also become entangled. Change the state of one, and the other responds instantly, even if they're light years apart. Einstein called it spooky action at a distance, otherwise known as quantum entanglement. In practice, it means that quantum computers don't just run faster, they think differently. Qubits don't follow one path through a problem. They explore all paths simultaneously. So, what does this have to do with space? Well, space is big. The size of the observable universe is approximately 93 billion light-years in diameter. Reaching Alpha Centauri, only 4.4 light-years away, with our current technology, would take thousands of years, even for the fastest spacecraft. If we want to travel beyond our solar system, to planets orbiting distant stars, or even galaxies, we need to overcome distances that break the limits of classical engineering. This isn't just a problem for propulsion engineers. It's a problem of computation. Designing advanced propulsion systems, like fusion drives or antimatter engines, requires solving quantum-scale physics problems that overwhelm even today's best supercomputers. With classical computers, modeling a single molecule's behavior gets exponentially harder as more and more atoms are added. Quantum computers, on the other hand, can simulate molecular interactions in real time. That means materials we haven't even imagined yet, ultra-light, ultra-strong, radiation-resistant, could be discovered and tested before we build a single prototype spacecraft. But let's go deeper into what that would mean. Imagine spacecraft hulls that heal themselves after micrometeor impacts, spacesuits that adjust to temperature, pressure, and radiation in real time, advanced engines powered by reactions we still barely understand. To navigate space efficiently, we need to optimize thousands, sometimes millions, of variables simultaneously: trajectories, fuel loads, energy conservation, life support, radiation, and shielding. These are optimization problems. This is where quantum computing excels. One example? D-Wave, a quantum computing company, has already partnered with NASA to test quantum optimization for scheduling and spacecraft pathfinding. In space, every ounce of fuel counts. Every second of delay matters. Quantum optimization could shave years off interplanetary missions and make crude interstellar travel mathematically feasible. And that's just for the engineering. Let's talk survival. Dangerous radiation, cosmic rays, DNA damage. Human bodies were not made for space. But what if we could predict, in advance, how each person's genome would respond to space conditions? Quantum computers could analyze vast genomic datasets and simulate those mutations before they happen. Pair this with CRISPR, quantum computing and AI, and you don't just protect astronauts, you preemptively edit resistance into their biology. It's speculative, but not science fiction. Not anymore. And speaking of biology, colonizing space means building closed-loop ecosystems, agricultural systems, environmental control, and systems where waste becomes fuel. These require precise ecological modeling, another quantum sweet spot. Quantum models could simulate entire ecosystems at once, accounting for variables like nutrient flow, microbial balances, and genetic drift. They could help us design critical plant cultivation systems to provide food, oxygen, and other resources for long-duration missions. Now, here's where it gets better. Some scientists believe quantum computing could one day help us crack faster than light travel, or at least, the theory behind it. Take the Alcubierre drive, a theoretical propulsion concept proposed by Mexican physicist Miguel Alcubierre in 1994. Inspired by Einstein's general theory of relativity, Alcubierre suggested that faster-than-light travel might be possible by warping space-time, compressing space in front of a spacecraft, while expanding it behind, like riding a wave through the fabric of the universe. But there's a catch. The mathematics behind this idea are incredibly complex. They require us to manipulate exotic matter with negative energy density, something we've never observed in a usable form. Worse still, solving the equations that describe this warp bubble demands computational power, orders of magnitude beyond even today's most advanced supercomputers. This is where quantum computing enters the picture, not as science fiction, but as a tool that could actually handle the unfathomable calculations necessary to simulate, optimize, and maybe even one day stabilize such a drive. In short, if the Alcubierre drive is ever going to leave the whiteboard, quantum computing may be the only computer powerful enough to get it done. But quantum computers could make simulating these warped geometries possible. They might not build the drive directly, but they could let us explore the math and test the limits of physics in a virtual sandbox. Think of it like this. Before we built rockets, we had equations. Quantum computing may be the pen and paper for the next leap in the engineering of advanced propulsion. There's another wildcard in space exploration: alien signals. If we ever intercept a message, or think we have, analyzing it will require more than brute force. It will take pattern recognition across unknown languages, unknown physics, maybe even unknown math. AI-powered quantum systems could sift through cosmic noise to find those patterns, and maybe, just maybe, detect an intelligence unlike our own. But let's not romanticize it too much. Quantum computers are still in the early stages of development. They require cryogenic temperatures, are prone to error, and we haven't cracked the code for scalable, fault-tolerant machines. Progress is being made. Companies like IBM, Google, and Rigetti are racing to build stable quantum processors. Diamond defect qubits, silicon-based qubits, and light-based quantum computers are being explored. Room temperature operation is crucial for scaling up quantum computers, making them more accessible and reducing energy costs. And even though we're not there yet, the learning curve is exponential. This isn't a question of if, it's a question of when. But here's the twist. As we stand on the edge of becoming an interplanetary species, maybe the real question isn't just what we'll use to get to the stars, or how we will do it. The question is, what do we take with us? Do we take our best? The ideals of cooperation, knowledge, kindness, and peace? Or do we pack up our fears, our hierarchies, our tribal instincts, and spread them across the cosmos like seeds? Some imagine a future like Star Trek, a utopian federation where humanity has transcended its divisions and pursues science and exploration for the greater good. But from an historical perspective, when humans have ventured into new frontiers before, whether across oceans or continents, we brought more than ships and flags. We brought systems of power. Totalitarianism, technocracies, hierarchies, exploitation, genocide, the list goes on and on. History is filled with examples. The colonization of the Americas, the destruction of indigenous cultures, the carving up of continents for profit. Exploration often came wrapped in ideals, but unfolded in violence. In that light, the tools we're building now, artificial intelligence, quantum computing, genetic engineering, they're not just keys to new frontiers. They're mirrors. They reflect who we are, what we value, and what kind of civilization we want to become. These machines are rare, expensive, shrouded in complexity and immensely powerful. And the more powerful the tool, the more it reflects the hands that wield it. So we should ask ourselves, as we build this technology to leave the Earth behind, what parts of ourselves will we bring with us? Do we carry the same old shadows, greed, division, short-term thinking? Or do we choose to leave them behind, like worn-out tools from a more primitive age? Will we take only our brilliance and compassion, our curiosity, our care for life, our hope? Because maybe the real question isn't whether we can escape Earth's gravity, it's whether we can escape our own. As we look ahead, past the red dust of Mars, beyond the cold light of Alpha Centauri, into the vast silence between galaxies, we face more than a question of distance. We face a question of who we are, and what we're becoming. Because it won't be steel, fire, or electrons that carries us across the stars. It'll be our minds, our souls, the models we build, and the futures we imagine. And in the quiet moments between invention and ignition, we'll have to decide, do we carry forward the shadows of our past, or the light that we've always wanted to become? If this sparks something in you, please like and subscribe. We explore the edge of what's known, and what it means for the future we're building. Drop a comment. Share your thoughts. Because the questions don't end here, they're just getting started. Welcome to the Metafiles.